For this learning module, we'll look at Newton's three laws of motion along with the law of gravitation. One thing that I wanted to say is this isn't a physics course, so we don't have a lab component, but if we did, we could actually take data and verify each of these three laws. That's what it means to be empirically validated. Another just quick note to mention, if you've had more advanced physics courses, you might be familiar with the fact that these laws are only valid if we're observing the object of interest from a stationary, inertial, or reference frame, meaning that we either have to be still ourselves or we have to be moving at a constant velocity. Those two assumptions won't be valid for us. We'll just always assume that they won't be relevant for us, I should say. We'll assume that we're working on observations taken from a stationary reference frame. The three laws that you probably remember, I'm sure you've seen them for a very long time. The first is the law of inertia, and maybe you've memorized this as the idea that a body that is at rest tends to stay at rest or something like that. But what really are we saying? Well, what we're saying, the way your book words it, is if there is a balanced force acting on an object, and what would be the opposite of balance? Well, the way that they're referring to it now, it would be imbalanced. What does that really mean? What we mean is that all objects, because they have mass, as we'll see on the next slide, they always have forces acting on them, right? And if the object is stationary, in addition to the mass, which tends to attract it to the Earth, in addition, you have forces that are counterbalancing that and holding it stationary. So as long as all of the forces that add on an object, from a vector point of view, add to zero, meaning that all those there's individual forces, the net force or the resultant force is zero, the body's velocity won't change. So that's the idea of inertia. The second law is just a very specification. Well, what happens if there is a net force? What if all the forces acting on the body don't tend to cancel each other out and there is a resultant or net force, or in the book's term, the forces are unbalanced? Well, in that case, the body will accelerate in a manner that's inversely proportional to its mass. So going back to those fundamental physical quantities that we talked about in the first learning module, mass just describes how much stuff is in an object. Well, you can think about it here. It's what tends to give the body inertia. It tends to oppose motion. When we have forces acting upon an object, depending upon how much mass it has, that will determine the amount of acceleration that we realize. Now, we're using a lot of technical terms here. What does it mean to accelerate? Well, fundamentally, it just means to change speed. So if we are not moving at all and we change speed, we're going to go into moving. So from a static point of view, clearly we're going to be dealing with scenarios where the acceleration is zero. And just to re-hit this point again, because it's very, very important, this doesn't mean that we're necessarily stationary. It just means that our velocity isn't changing. And I should have, and maybe I'll in the next slide, set of slides, do kind of a more formal definition of the kinematic quantities. But velocity, of course, is just the integral of acceleration. So when we have a body which is accelerating over time, it will tend to have a velocity which is changing. Newton's Newton's second law. One thing to note here, and I should have covered this a little bit earlier, one of the two ways that you can denote a quantity as a vector is by actually typing it in boldface. The other way that's kind of easier if you're writing by hand is to put a little arrow above the quantity. And when we get to that point in the course, I will do that. But if you notice here, what we really have is kind of what you call a scalar relationship between two vectors. So mass isn't a vector quantity, as we said in the previous learning module. So when we have F equals ma, F and A are both vectors. What we know is that both F and A will be aligned in the same direction. So they're related by proportionality in terms of their magnitude by the mass of the object, but the direction is the same. And what does that mean physically? That means when we apply a force to an object, we can control the direction in which the velocity is changing. Newton's third law, the law of action and reaction, basically says if you have two objects which are interacting with one another, they exert forces on each other in equal and opposite directions. So if you view my left hand, and yeah, it's my left hand, acting as a force on my right hand, even if we're stationary, even if we're not moving, if the left hand is pushing the right hand by just say, 10 pounds, in that particular circumstance, the right hand is also pushing the left hand by 10 pounds as well. And that's kind of best visualized by this, in terms of magnitude, best visualized by this drawing that we have here at the bottom, which I've denoted as being R3. In terms of the terminology, it's all depending upon your point of view. Whichever force you call the action force, which is object A acting on object B, the reaction force has the same magnitude. It's just directed such that it's object B acting on object A. So just kind of keep those in mind. This is an engineering class. I'm not going to ask you a lot of definition type problems, but kind of having this walking around language is really important. And if you can do the work now and kind of conceptualize these concepts, it'll make things easier. The other thing that I did want to point out, sorry for this, is if you want some visualizations of the first two laws, I took this figure from the textbook. You can notice in the first case what they're trying to emphasize is that a body can be at equilibrium. So lots of different ways to say this. Equilibrium means, in their terms, a balanced force. It also can be said as no net force or no resultant force. So you can't have a body that has multiple forces acting on it. However, if the directions and magnitudes are such that these vectors sum to zero, right, by Newton's first law, this object will maintain whatever velocity it had beforehand. So if it was moving to the right, it'll continue moving to the right in spite of these forces acting upon it. So that's what that first figure means. The second figure means, in this case, we look at the kind of object of reference, which is just a ball here. Clearly, if we have a force pushing to the right and no other force, there's going to be an unbalanced force or a net or resultant force. And in that case, the speed of this object will change. Particularly, it will accelerate. Notice that acceleration is a vector that's also kind of co-aligned with the force vector. They're calling that accelerated motion, and we already talked about figure C. So after Newton had those three laws in hand, he kind of postulated the law of gravity. And what gravity refers to very generally, so we tend to think about it on a planetary scale, and we'll talk about why that is in a second. But in general, if you have two objects and both have a mass associated with them, and they're separated by some distance in space, they're going to tend to interact with one another. Particularly, they're going to tend to exert attractive forces on one another. And the nature of that attraction is given by what's known as an inverse square law here. So what F is, and F is boldface because it is a vector, that will describe the tendency of objects defined by mass m1 and mass m2 to interact with one another, particularly if they're separated by some distance r. The magnitude of the attraction or the magnitude of the force will be inversely proportional to the square of that distance, and it will be proportional to the individual mass values. Now, if I say that, you might say, well, I have a mass, the computer has a mass, but I'm not flying at the computer right now. Why is that? Well, it turns out that this constant of proportionality g here is on the order of 10 to the minus 12th in terms of the standard SI units of force, which are newtons, which we'll cover a little bit later. Now, what does that mean? Well, if you think about scaling a quantity by 10 to the minus 12th, in order to see, and you additionally have that 1 over r squared factor that you're dealing with, and if you think about what that means, as the distance between the two objects increases, that force will get smaller and smaller and smaller in an inverse square fashion. So both the constant of proportionality and this 1 over r squared law are going to tend to make this force small, but really the thing that really makes it small, as we'll see in a minute, is the constant of proportionality, as long as the masses are not terrestrial. So the one thing I wanted to point out, I know that some of you are taking physics 2 right now, and you might say, hey, if you make that G a K sub E, that looks a lot like Coulomb's law, which describes the tendency of objects to interact with one another, not because they have mass, but because they have charge. And that is, in fact, the case. Coulomb's law, from a formula point of view, looks a lot like Newton's law of gravity, only difference being the m's are q's, meaning it's not the fact that the objects have mass that makes them interact. It's the fact that they have some net charge, right? We only observe electrostatic phenomenon when there's a net charge. So if you think about it, that the same thing that gives all bodies mass, the fact that on the atomic level, it's made up of individual atoms, and atoms consist of some subatomic particles, protons positive in the middle, electrons in the valence area around the outside. We don't see a lot of electrical phenomenon in our daily life because, by and large, most things, for every plus that it has in the nucleus, it has a minus on the outside, and it's net neutral. Particularly what I'm getting at there is this constant for Coulomb's law of electrostatics is much larger than for the gravitational case. So key point being, you only see electrical phenomenon a lot, even though it's a strong force, because most things are neutral. absent of like rubbing your feet on a carpet and actually transferring some charge via friction and getting some static electricity on you, then you see it. But the majority of the time you're neutral. You don't see gravitational very often, other than in the case of Earth, because the constant of proportionality is so small that it can only be overcome when one of those masses is very large. So getting to that point, let's talk about this concept of weight. So if you're talking about the interaction between any object, say it has mass m, and the Earth, say it has mass big M sub e, we can customize this formula, right? And if you notice, all that I did here is taken, right? M1 is M and M2 is ME. So as we said previously, ME is the mass of the Earth there. M is just the mass of whatever object we're talking about. Well, so again, we have, say, in the case of me, myself and the Earth, and I have mass and the Earth has mass. And our centers of mass, which we haven't really defined yet, are separated by some distance, some very large distance, because the Earth is a very large planet, of course. So Newton's third law, so Newton comes up with this law of gravity after he comes up with his first three laws. And the third law says that, hey, if there's a resultant force acting on an object, that object should accelerate. And Newton's law of gravity says, hey, if two objects have mass and they're separated by a distance, they exert force on one another. So what that means is that just because I'm in the presence of the Earth, I should be accelerating. And how would that look? Well, if I take my law of gravity, which has been customized for the case of the Earth, and I equate it to Newton's third law, what I notice is that I can define an acceleration that's associated with nothing else than being in the presence of the Earth, according to this formula here. Now let's look at this formula here. We said that G is a very, very small constant, but ME, the mass of the Earth, is going to be very, very large. So when we multiply those two together, kind of the small proportionality constant effect will go away. And that's why we can actually observe the force or the acceleration associated with being in proximity to the Earth for the case of a large planet. What is r squared? Just to go over it again, r is the physical distance between the center of masses of the two objects of interest. So if I think about me versus if I were to hold this cup at some height higher than me, just assume for now that the center of mass is just physically, geometrically in the middle of all these things. Well, clearly, wherever the center of the Earth is down there, between like the center of me and the center of this cup, these heights are different, right? So that our quantity will in general vary depending upon where you're at on Earth, right? The relative height relative to sea level, along with kind of the elevation from the surface of the Earth. However, that quantity, that distance is going to be the sum of two things if you think about it. It's going to be like the sum of the distance from the center of the Earth to sea level plus whatever little variability I put in it on top. And if you think about that, whatever little variability we have in the height relative to sea level is going to be very negligible relative to the radius of the Earth. So for all practical purposes, you're going to be able to approximate that by a constant. That's what I mean by what is the variation with R. If you change the height of something relative to sea level, this R value will change, but it won't be an appreciable amount. So we can kind of approximate this by a constant. Another thing I wanted to say is in terms of the direction of this force, it's always going to be pulling me towards the center of the Earth. Because if you think about it, the direction of this gravitational force is always, we'll define this more formally later. The book's kind of weird. It like introduces some things before it introduces kind of some concepts that you need. But this R hat is going to be a unit vector directed along a line of action between the two centers of mass. So if I have a center of mass and I have the center of the Earth, which is its center of mass, that force will always be acting in that direction. And we'll formally define what that means later. But one thing I wanted to point out, you probably realize, hey, I've seen this derivation before, and this acceleration, which is due to nothing more than being in the presence of the Earth, I don't denote it by A, I usually denote it by G, and that's true. And what this approximation means here of 9.8 meters per second squared is that for all practical purposes, although this is a function of R, we can basically just approximate it as a constant. And what does that physically mean? Well, let's just, to make our math easy, make 9.8 meters per second squared 10 meters per second squared. I'm not going to drop my phone. I do it enough just on my own without using it as a demo. But if I did, what does 10 meters per second squared means? That means that every second this thing is in free fall. Right now, there's no net acceleration on it because although it does have an acceleration due to gravity. Another way to say it simply is it has weight. I'm counterbalancing that weight with my hand, holding it up. So there's no resultant force on it. But if I removed my hand, what would happen? Well, it would experience an acceleration due to gravity such that every second it's going to go 10 meters a second quicker. So after it's been in free fall for a second, it's moving 10 meters a second. After it's been in free fall for 2 seconds, 20 meters per second, so on and so forth. If acceleration is constant, velocity is increasing in a linear fashion because of that calculus relationship. So in summary, the formula that you're probably very used to seeing is that for the particular case of the gravitational interaction between an object and the Earth, we can call that force its weight, and it's just going to be proportional to this gravitational constant g, which the way that I've written it there is a vector. Its direction is going to be towards the center of the Earth, and its magnitude is going to be approximately in SI units, 9.8 meters per second squared. So let's go back to this example of the train wheel on the train track. Sorry, I wish I had better examples, but where I'm kind of starting late, I have to take some figures from the book in order to do this. So let's assume that the concentrated force, just as a recollection, what concentrated force means is although this force is exerted over an area, we're modeling it as being exerted at a single point. So let's assume that the force that's exerted by the rail on the wheel, so pointing in the upwards direction, is 500 pounds. So the first bullet says, describe the force exerted by the wheel on the rail and justify your answer with a physical law. So you have to read the problem very carefully to make sure that you get what I'm asking. So I'm saying the rail pushes up on the wheel by 500 pounds. Well, if the rail pushes up on the wheel, remember that the rail is in contact with the wheel. So if you go back to with the animations, it's a little bit tough, a bit sick, Newton's third law here of action and reaction. What this says is when two objects, including the wheel and the rail, interact on one another, they apply forces in equal and opposite directions and of the same magnitude. So in the case of our problem here, if the rail pushes up on the wheel, 500 pounds up, the wheel pushes down on the rail, 500 pounds down. And that would be Newton's third law for my justification. So bullet point 2, assuming the train is stationary, are any other forces acting on the wheel? Justify your answer with a physical law. Well, yeah. Because if that wheel, I should have said the wheel is stationary. If the wheel's not moving and there's 500 pounds pushing up, right, there must be another force acting on the wheel. And certainly one of those forces, in absence of other things, is just the weight of the wheel itself. And I can always determine that weight by just taking the mass of the wheel and multiplying it by the gravitational constant, as we just showed. So hopefully this can kind of give you some refresher, I'm sure, to these basic physical principles of Newton's 3 laws, which were inertia, F equals ma, action and reaction, understand kind of the Newton's gravitational law and the fact that you only see realizations of it when you're dealing with a mass that's really large like the Earth. And for the case of the Earth, in general, Newton's gravitational law is an inverse square law, G m1 m2 over r squared. G is small. We see it because one of the masses is big. And although r varies in general, since the predominant contribution to it is the radius of the Earth, we can pretty much just approximate it as a constant. So hopefully that made sense, and I'm going to call it a night for tonight, and I'll record some more videos tomorrow.